This video is going to talk about normal strain and deformation. So normal strain is little letter epsilon, and this strain is equal to deformation, which is little letter del over the original length. So again, this is deformation, and this is the original length. So strain's pretty simple. Deformation, by the way, is simply a change in length. And obviously we're talking about units for length. So for strain, our units are millimeters per millimeter because deformation is in millimeters and original length is in millimeters. Or we're talking about strain being in inches per inch because, again, deformation is in inches and original length is in inches. So it's either that we're measuring in US units of inches or we're measuring in SI units of millimeters. Technically, you might not have the original length in terms of millimeters, but do just make sure your units match up when you're doing this. So either way, strain is going to be a very small number. It is going to be a very small number. It's usually not very big. So normal strain is caused by, as we'll write it over here, it's caused by normal stress. So again, remember that was normal stress is equal to the load over the area. So that is caused by our load. So a load technically does cause stress. That stress does cause strain, which is ultimately leading to deformation, which makes sense. You put a load on something and it obviously deforms. How much it deforms is based on material properties, but for now, that's all it is. So we're just going to pop right into an example. So in our example here, we have two rods, A and B, kind of irrelevant what their sizes are for this example because we're going to be dealing with the strain. But we have these two rods, A and B, and they're connected to some block C, and the block C has a weight, and this weight is hanging on these rods, and that weight is going to cause a strain in AC and a strain in BC. It's going to be the same amount. It's going to be 250 times 10 to the negative 6 millimeters per millimeter. And what we want to find is the elongation of AC and BC. We want to see how much they're going to stretch. So for strain, elongation does mean positive, and shrinking is negative in terms of strain. So you can see our strain value is a positive 250, and that's because they are elongating. So this is causing it to get longer. So again, all we really have to do is write down our equation, and that is that strain, which we have as 250 times 10 to the negative 6 millimeters per millimeter, is equal to the change in length, or how much it's going to elongate, over the original length. And what is the original length for AC? For AC, the original length is, that's a 3, 4, 5 triangle, right? 3, 4, 5 triangle here. So that's literally just going to be 5 meters. So just plugging that in, if I want to actually solve for the elongation of AC, that's just going to be 250 times 10 to the negative 6 millimeters per millimeter times a length of 5 meters. Now you might be thinking, oh no, the units, they're not matching. Technically millimeters per millimeter is going to cancel. So what I'm going to get is a value in terms of meters for this. So yeah, that's going to be really tiny. If you don't want a value in terms of meters, if you want it in millimeters, then fine. We'll just multiply by 1,000 millimeters and 1 meter, and these units will now cancel, and I'll be left with millimeters. It's kind of up to you with what you want. So there we go. So ultimately, we're going to get that the elongation here of our rod AC is 1.25 millimeters. Yes, it's so small that if you were looking at it, you wouldn't even notice it. Right? You can't really notice 1 millimeter of difference, which is pretty typical if you're thinking like some pretty thick steel bars or whatever. It's not actually going to elongate too much, and that's kind of like what's expected. So strains are usually really small values, unless they're things like rubber, where like a rubber band is going to stretch pretty darn far. Other than that, they're going to be pretty small. But that was just AC. Now we're going to do it for BC. It's kind of the same exact thing. The only difference is that BC is not the same kind of triangle. Does this make much sense? Maybe not. Maybe if it's a different material, it'll stretch a little bit farther. Who knows? But here we go. Same thing. We have that the strain is 250 times 10 to the negative 6 millimeters per millimeter. And that's equal to the deformation I want to find now for BC over the original length. Now this is technically it's a 1 square root of 2 triangle, or it's, in this case, 4, 4, and then 4 times the square root of 2. So technically our original length is not that. It is 4 times the square root of 2. If you don't believe me on that one, it's technically 4 squared plus 4 squared, which is the square root of 2 times 4's squared. The square and the square root are going to cancel. The 4 pops out, so it's 4 root 2. That's where it came from, in case you don't remember it, but I think we pretty much know trig here. So we get that the deformation of BC is equal to, again, if we're turning it into millimeters, doing the same thing we did before, 250 times 10 to the negative 6 millimeters per millimeter times 4 square roots of 2. That's, of course, in meters, by the way. That's in meters. And if you don't like it in terms of meters, then multiply by 1,000 millimeters over 1 meter. Those units are going to cancel. This unit's going to cancel with that unit. I'll be left with millimeters. So at the end of the day, if you want it in terms of millimeters, it's 1.41 millimeters, which again is relatively small. So again, strain's really simple. It's just a change in length over an original length. Remember that the change in length here is technically not how much it has elongated, but this is simply the amount of change in length. It was technically, that change is equal to the final minus the original. So, I mean, yes, it is the change, but if you wanted to find out what the length of it is now, then you just have to go one step further. So just, be careful with it. It doesn't exactly matter how you want to write it. If you want to write strain is equal to del, or maybe perhaps you want to write strain is equal to delta L over L naught, or maybe you want to say it's L final minus L original over L naught. It's all the same. Strain, at least for normal strain, is very, very straightforward.